just a few words to myself. My name is Marcus. I'm with MSG since 2001 in a variety of roles, from a software developer over leading the maintenance team to being part of the product management right now. As part of the product management, I'm coming more from the practical and business side of things, so I'm not going to discuss any algorithms protocols with you today. So it's more or less a high-level introduction to the topic. I'm also not going to discuss any investment tips on Bitcoin. I am not able to predict the course of Bitcoin or any other cryptocurrency in the near future, and I'm also not going to discuss the next big initial coin offering. So it's about the technology, about some misconceptions around blockchain, and how all that stuff works together that the media reports about. So first things first, blockchain hype. So that blockchain topic came up around the year 2008 when some guys, or a single individual that's not really sure, under the synonym Satoshi Nakamoto, provided a paper, and in that paper there was a detailed explanation about how cryptocurrencies could work, how Bitcoin could work, and on how to deal with the specific problems of blockchain technology and peer-to-peer frameworks in general. So it was mainly about how to avoid double spending in those scenarios. It was about how to gain trust between anonymous participants in peer-to-peer networks when it comes to financial transactions. And with that paper, the hype basically started. So what was proposed in that paper wasn't really something new. It was basically old technologies recombined. So it was a bit of hashes, it was a bit of peer-to-peer networks, it was a bit of asymmetric cryptography, and all that brought together, recombined, made up blockchain. With that initial spark, that idea gained momentum. And as you can see here, on the left side is the Google Trends for the search term Bitcoin, and it started to really take off in 2015. And of course, Bitcoin is also on the Gartner hype cycle, where it slowly moves towards the right side, towards the plateau of production. So it's one of the most hyped buzzwords in the last years. That can also be seen as a lot of mass media start to report about it. Mainly their reports are around cryptocurrencies at the moment, around Bitcoin. Even our beloved Passauer Neue Presse had a huge article about that today, but also other big German media are reporting about that. So in this session, I'm going to deal with some of the misconceptions around blockchain. That's the initial point of my talk. And afterwards, we'll get into detail about some technology behind the blockchain and how all that stuff that the media report about goes together. So let's start with demystifying some of the misconceptions. As I'm not sure about the audience, we start really slow and then gain momentum. So the first misconception I wanted to talk about is blockchain and Bitcoin. So blockchain is not the same as Bitcoin, even though it sounds like it when media talks about it. It's not the case, it's not the same thing, and both things are not synonymous. Blockchain refers to technology stacks, to protocols, to the infrastructure, and also to APIs and algorithms. So blockchains themselves are the technology basis for blockchain applications. Bitcoin is one of many cryptocurrencies, and it's just an application built on blockchain technology. So one could think of the TCP/IP protocol, which is the basis for the internet. So blockchain would be something like the TCP/IP protocol, where Bitcoin is just an application built on that protocol. So like a web browser or WhatsApp Messenger that's using TCP/IP below their user interface. It's the same with Bitcoin and blockchain. Another misconception that one can read of a lot is the fact that media always talks about the blockchain. So the blockchain as a game changer, the blockchain as being a cool thing. But in fact there is no the blockchain. There are many blockchains, and one needs to differentiate between the technical things, the technical view to that topic, and to the business view or the application view to that topic. So there are a lot of blockchain stacks which are the foundation to blockchain applications. So here in my example you can see some of them like Corda, Hyperledger, Ethereum or Tendermint. And on the other side of the spectrum you have blockchain applications which are built on those technology stacks. So each of those blockchain applications are in fact blockchains by themselves. So there is not a single blockchain, there are thousands of blockchains out there. Some of those blockchain applications are bigger, some of them are smaller, some of them are commercial, some of them are proof of concept. And the same goes for blockchain stacks. Some of them are huge projects backed by IBM or by the Linux Foundation. Some of them are just, well, small freeware tools, and when you're trying yourself to create a blockchain application, you're basically free to use, free to choose from the spectrum of blockchain stacks. And each of them has specific functionalities to provide specific API-specific functionality which other stacks don't have, but in fact there is no single blockchain out there. The next misconception I want to clarify is that we already know what blockchain technology is good for. So there is this new shiny toy called blockchain, but in fact we don't have that breakthrough commercial and business scenario at the moment. So there are a lot of proof of concepts, there is Bitcoin, there are some other cryptocurrencies that use blockchain, but the big commercial breakthrough is not there yet. So usually in IT we have something, we have a situation like the one you can see there. You have a business problem, and then along comes IT. To solve that problem, we apply IT and get to a nice solution. In our blockchain world, it's basically the other way around. So we have a new toy in our hands, which is called blockchain, but we are somehow lacking the problem to solve. So we solved that Bitcoin thing, but in a commercial perspective, in a commercial scenario, there aren't really any big tools, products on the way to solve anything. So it's a bit like in Indiana Jones' Raiders of the Lost Ark. So everyone is trying to find the Lost Ark, and in our case it's the lost blockchain business case where anyone can really earn money. So that's not there yet. Commercial use cases are really limited at the moment. Big parts of the industry are just waiting for solutions to come. Other players are investing money in proof of concepts, but there isn't really anything in production yet. Very interesting is that we had a meeting with one of the Amazon Web Service managers a while ago, talking about blockchain, and he told us that people always approach him and ask him if they can buy a blockchain from Amazon. And then he goes along and asks them, yeah, well, of course you can buy blockchain from us, you can buy blockchain technology from us, but what is your use case? What are you going to do with that blockchain? And they usually answer, well, I want to do the same thing as Amazon does with multi-blockchain. And this shows that there isn't really an idea what to do with it. So people have no clue what to do with it. Of course, there are some scenarios, some relevant scenarios when blockchain could help to solve problems instead of creating new problems. So what are relevant scenarios? So when you look at different scenarios, you could have scenarios where you have multiple parties and multiple users collaborating. If you have something like that, it makes sense, it might make sense to look at blockchain. What definitely doesn't make sense is selling a blockchain to a single client. So selling an in-house blockchain to a company really doesn't make sense, because what you need are a lot of people collaborating and sharing information. What relevant scenarios should show is no level or very low level of trust between all the participants. And this is something we see in Bitcoin, where we have a lot of anonymous parties and a lot of anonymous nodes exchanging financial transactions, and they don't know each other, they don't trust each other, and if you have a scenario like that, you could also use blockchain. When you look at the industry and look at businesses, you usually don't have that. So players, different companies usually trust each other, and so this is a thing which is not relevant for them. Another thing that's interesting when you look at use cases is that there's no single authority that controls the blockchain. There's no single authority that controls the collaboration. In a scenario where you don't use blockchain, a single entity could control databases, a single entity could control access to the network. And if you want to avoid a single entity pulling the plug on your network or your application, you could also look at blockchains to solve a problem at hand. What's very important is the fact that in a blockchain world we talk about full transparency in our network. We talk about immutable entries in our blockchain and a single source of truth. If you have a scenario where you exactly require this property, then that could also be a relevant scenario for blockchain. We learned that this transparency thing and this immutable property usually causes problems in a business context, because people say, well, I don't want to have everyone seeing the same thing, because I have private information and this information should stay private. And of course, I want to be able to change things in my database. So when it comes to business context, this is really problematic. But it can solve a lot of problems if you apply blockchains in this context. When you think about the insurance industry, where we still have paper-based information exchange, where we have paper going back and forth, where you have a lot, it makes sense to have one single source of truth and everybody being able to access that single source of truth. And another thing is that your scenarios should have a very low level of complexity. So blockchain isn't a good thing when you have very complex business cases you want to solve with it. Of course, you can have so-called smart contracts in your blockchain that automatically run business processes, but those are merely yes or no decisions, or checking for some trigger values, or checking external data sources, and doing, well, static handling of data, creating new transactions in your network. It's not really something that will come to mind when you think of complex business scenarios. What does all that mean? The industry is still looking for cool business cases and use cases. And it's not just use cases, it's also a way to earn money. Because there are ideas, there are use cases, but no one is really earning money with that. So, from a technical perspective, or in short words, blockchain in a nutshell. So when it comes to blockchain, we are talking about a distributed IT architecture, meaning there is a peer-to-peer based network, and in that network nodes are sharing processing power, and nodes are also sharing storage. And if you add asymmetric cryptography, you get the possibility to store immutable records, you get the possibility to verify transactions in that network, and in the end you get secure transactions. And in result you get something which is called blockchain, or simply distributed ledger, and that is from a technology perspective, a chain of blocks, chain of transactions linked together, transactions are timestamped, and you get an immutable distributed ledger. Or, as Wikipedia states it, blockchain is a distributed database that maintains a list of ordered records which we call blocks. Each block contains a timestamp and a link to the previous block. And by design, blockchains are resistant to modifications of data because they are linked together and because of some properties we see later. And once recorded, the entries cannot be changed easily. So they can be changed, blockchains can be forked, data can be altered, but in theory they cannot be changed, at least not easily. So in the following, we're going to look at each of those building blocks in more detail to see what all that means. Okay. So the first building block we have in our blockchain universe is the fact that we are talking about the distributed IT architecture. That architecture, so this is the one on the right side, where it says distributed. Architecture ensures that there is a distribution of storage space and also distribution of processing power in a blockchain network. And it's based on peer-to-peer technology, so we don't have any centralized instance or centralized authority that could pull the plug on our nice network. Which means it's very robust against attack vectors, so nobody can pull the plug, no central authority can change data. As usually every node in that network holds its own replica of our blockchain. So there is no single instance, no single database. It's really a distributed ledger. And if one of those nodes stops existing, the network still exists. So there is no possibility to just disable the network by disabling one node. Coming from that, in a blockchain there can be different types of nodes. When we talk about the blockchain network, we see three different types of nodes, but usually the other blockchain stacks also provide some sort of node differentiation. Most of them are coming back to those three types. So there is a very simple type of nodes which we call wallet. A wallet, has a private key and an address, and it controls unspent transactions. A wallet also owns assets. In a Bitcoin world, those assets are transactions or Bitcoins, but those assets can be everything. And a wallet can also send assets in form of transactions, and when the wallet or a wallet user does that, transactions are getting signed and published to the network. A full node is a very important thing because a full node maintains the complete blockchain. That means it maintains a copy of that blockchain, a local replica. A full node also validates transactions and blocks to make sure they are actually valid and legit in that sense. And a full node also relays or propagates new transactions and blocks to the network. And then we have a thing called miner. A miner does the same thing as full node, but in addition, the miner collects transactions, assembles them to blocks, tries to provide a proof of work. What that is, we see on one of the next slides. And the miner also gets rewarded for new blocks. That's basically where bitcoins come from in our Bitcoin network. All that stuff is held together by asymmetric cryptography, which isn't really anything new. It's rather old. But as I said, blockchain is just a recombination of already existing things, so it makes sense here. So what does asymmetric cryptography means? It means that messages are encrypted, decrypted, or signed using a pair of keys. A public key, which is public, so everyone can possibly know about that key, and a private key, which is only known to the sender of that message, in our case, the owner of that wallet. So why is that cool? Because we can do two things with it. The sender can use the receiver's public key to encrypt messages, and the receiver can then use its private key to decrypt messages. So this is one cool thing. And the next good thing, or the next cool thing, is that the sender can use its private key to sign a message, and the receiver or anyone having the public key can use the public key to make sure the message really came from the sender and the message wasn't altered in any way. In our blockchain world, private key and public key are created when a user's wallet is created. So there is one private key associated to a user's wallet. And there's also public key associated to a user's wallet. The public key is usually a hash of the wallet address. So what happens now in our blockchain universe, when transactions are sent to the network and the sender signs those messages with its private key, and any member of the network can then use the public key of that node or of that sender to verify that, that message, that transaction, to make sure it really originates from where it says it comes from. And this brings us to the next building block, which are hashes. So hashes, what is hashing? Hashing is basically fingerprinting for data. You put in some input, use a hash algorithm, and if you do that, you always get exactly the same output. The output is basically a shortened version of the input, which usually has a fixed length. What does that mean? Applying the same hash algorithm to the same input always leads to exactly the same output. And if I only change one bit of the input, as in my case here, as you can see, in the first sentence, the A by A lazy dog is small, it's not in capitals. And when you see it in the second box, it's in capitals. And as you can see, the hash value calculated is completely different. So, why is that important? We need that to verify information in our blockchain. So when the hash value and the hash algorithm is known, and we have a given input, we can calculate the hash of that given input, and then we compare different hashes with each other, and by doing that we can verify that the original information wasn't changed. So those four building blocks are basically the foundation of every blockchain. And on the next slide we're going to discuss how all that works together. Okay, so the first thing we have in our blockchain are transactions. Transactions can either be financial transactions, like in a Bitcoin network, but transactions can really be everything. So it can be securitized representations of real-world assets like land deeds or diamonds you want to transfer on your blockchain, but can also be just an entry to your distributed database or really any other asset that you can think of. So how does that blockchain thing come to life? So in my case, let's assume node A wants to send some asset to node B. So what does node A do? Node A creates a transaction and signs that transaction with its private key, and then the transaction is published to the blockchain network, to the peer-to-peer network. The network publishes the transaction to nearby and neighboring nodes, full nodes of my node A. And the next thing is, or the first thing is, those nodes do, they verify the transactions. So by using or by having that asymmetric cryptography at hand, they can verify that this is really a ledger transaction coming from my node A. And another thing they do is they propagate the transaction to something called memory pool. A memory pool in the blockchain network is the place where all those transactions are stored before they are pulled and assembled to blocks by miners. And this is the next thing that happens. A mining node pulls transactions from that memory pool, assembles them to candidate blocks, verifies the consistency of those blocks, verifies the consistencies of those transactions, and provides a proof of work. And after the proof of work is calculated and we are sure that that block is consistent, those nodes add a new block to the network, to the blockchain. The fastest node in calculating proof of work usually wins and is allowed to add new blocks to the network and gets bitcoins in the Bitcoin network, for example, as a reward for calculating the proof of work and adding that new entry to the blockchain. And after that is done, the mining node is done, our block and our new truth of our blockchain is propagated to the network again, where it's picked up by full nodes, and they verify the new state of the blockchain, they verify the created blocks, and propagate those new blocks, the new status of the blockchain, to other nodes in our chain. In that step, those nodes also add those new blocks, the new blockchain truth, to their local replica of the blockchain, and they also make sure that the memory pool is updated. So transactions already added and assembled to blocks will be removed from that memory pool. So, as we now know how single transactions move through the network, we should have a look at single blocks in that blockchain, and also the blockchain itself. In general, blocks in the blockchain consist of two parts. They consist of a block header and a collection of transactions. And that block header contains a lot of administrative information, but it also contains two very important hashes and a timestamp and a nonce field. So the first hash that is contained in our blockchain header is the hash of all hashes of all transactions belonging to that block. So why do we do that? So we do that to ensure that the network can always verify the integrity of a block and of the transactions belonging to a block by simply recalculating hashes and comparing hashes to each other. The second important hash value in the block's header is the hash of the previous block. So this information links together the chain, the blockchain, and basically ensures the immutability of our blockchain. So you have to keep in mind that the hash of the previous block is also part of the hash of our current block. Meaning, if the hash of the previous block changes, the hash of our current block will change, and the hash of the previous block will change if some of those transactions in there will be altered. And this ensures that no single entity, no single attacker is able to change our chain, because if one of the transactions in the previous block would be changed, all succeeding, all following blocks will be changed as well, or will change as well, hashes will change. So this is basically the thing that holds the structure of our blockchain together. And the block header also contains a nonce field. And that nonce field is related to our proof of work, the proof of work I've been talking about a while ago. So what is a proof of work good for? So in order for a block to be accepted by the network, miners must complete the calculation of a proof of work, and during the calculation, all transactions belonging to that block and also the value in that nonce field are considered. So that proof of work is required to ensure the consistency of the blockchain and to ensure that blocks and transactions are legit. So how does that thing work? Basically, the calculation of a proof of work is a random process. In a Bitcoin network, for example, the proof of work consists in finding a hash for the current block, where that hash starts with a given number of zeros. And the amount of number of zeros, or the number of zeros that the hash has to start with, is defined by the network itself. So the network adapts according to the processing power available in the network, and gives every mining node the task to find a hash with a certain number of, starting with a certain number of zeros. So what does that have to do with the nonce field? Well, basically, the mining node fills the nonce field with different random numbers, and with brute force and trial and error, calculates hashes for that header, including, of course, the changed values in the nonce field, and does that as long as the correct pattern was found. So as long as the hash ends up having a given number of zeros, required by the network. Using that brute force method, of course, takes a while, takes a very long time to come up with a hash that fits or matches the properties which are required to prove that work. And but on the other hand, with having that hash and with knowing the hash function, it's really easy to make sure that block is valid, because the only thing a full node has to do is taking the block header, including that nonce value that the miner came up with, calculate the hash, and compare it to a given hash. And if the pattern matches, if the hashes match, if there's a correct number of zeros in that hash, the block is verified and legit and can be added to our blockchain network. So as I already said, in a Bitcoin network, this is where new Bitcoins are created at that point of time. And the Bitcoins which are created by calculating the proof of work can basically be seen as a reward for providing processing power. So the miner is getting paid for having invested in CPUs, graphic cards, Chinese hardware, and of course the energy that was required to calculate those proofs of work. And this is also one of the properties that's often criticized in media, because media says, well, it's so expensive to calculate those blockchains and work with those blockchains, and it uses up so much energy, and it's a waste, and do we really need that? Well, in fact, this type of proof of work is just one form of proof of work. So there are other forms like proof of stake, or maybe your blockchain doesn't require proof of work at all. So when you think of blockchains in a commercial context, you might trust every participant in your network, and if that's the case, you don't really need that proof of work, and you don't need that computational power, and this isn't really a hurdle for broad and wide use of blockchains, even if it sounds like it. So, now we have transactions, blocks, legit blocks, and we link them together. Now the question is, how do we come up with our true version of the blockchain? So how do we decide which version of the truth is basically the truth? To do that, there are some simple rules. So in a usual scenario, in the scenario we've just seen, there are mining nodes. Each mining node creates its blocks, adds those blocks to the blockchain. The fastest mining node wins. But things get a bit more complicated if two mining nodes come up with a solution of the proof of work at the same time. And to deal with situations like that, there are three simple rules in our blockchain universe. The first rule is that only valid blocks become part of the blockchain. So our full nodes, by comparing hashes, by making sure the correct number of zeros was found, by making sure the proof of work is there, make sure that only legit blocks are added to the blockchain. So if that's not given, the block will not be added. The second thing is, as all blocks are timestamped, the fastest block will win. So if we find the same block at the same time, the one that's the miner that's faster wins. But in the rare case where we have two or more valid blocks with the same timestamp created at the same time, the blockchain branches like this. And then new blocks are created. Miners are finding new blocks, adding new blocks, and new blocks are added randomly to one of those two branches. Like in this example, to the branch on the top. And this now leads to rule number 3. Rule number 3 says that only the longest blocks will only be added to the longest branch of our blockchain. So in this case, if a block number 5 is found, it will be added to the upper branch, and the lower branch will be ignored from that point in time onwards. And with doing that, our blockchain is consistent again. So, where does that leave us? Basically, that's all there is when it comes to an introduction to blockchain. That's the magic behind blockchain technology. Of course, there are a lot more topics to talk about, like smart contracts and application in business, and double spending and tech vectors and all that stuff. But that should be it for today. So this is just a basic introduction. So let's wrap up. First thing to remember is blockchain is not Bitcoin, even if it's mixed up in media sometimes. In the same direction goes the fact that there isn't the blockchain. There are many blockchains, many different blockchains. And very important is the industry is still looking for applications. So when you come up with a use case, with a business case, chances are that you will find somebody buying your use case because everyone is eagerly waiting to find that thing, that golden cow to make cash. And from a technology perspective, the blockchain isn't really anything new. It's a mix of already existing technology recombined to make sense. And, well, distributed IT architecture and asymmetric cryptography are, in result, something called blockchain or distributed ledger. And that's it for today. Thank you for listening.